Welcome to this explainer. You know the exact feeling. You've been staring at a training loss plot for thousands of hours, and suddenly your model just flatlines. Or worse, it explodes. Today, we're putting on our mechanics hats to diagnose exactly why your model won't train. We're going to pop the hood and fix the underlying physics of your optimization engine, focusing on the absolute most critical component for modern convergence: momentum.
Okay, let's picture this physical bottleneck. Imagine vanilla gradient descent as a blind hiker trapped in a steep, narrow canyon. They take a huge step, bounce violently off the left wall, overcorrect, and smash right into the right wall. It's an exhausting, microscopic zigzag. Now, add momentum. Suddenly, your optimizer isn't a hiker anymore. It's a massive, heavy bowling ball. When it hits a wall, its sheer physical mass dampens the bounce. It completely ignores those narrow walls, smooths out the path, and just accelerates straight down the slope. This physical transformation is what literally saves your training run.
To get your training back on track, we'll quickly blueprint this diagnostic process. We're going to cover navigating the ravine, the physics of momentum, the velocity vector math, the PyTorch tuning dial, hardware memory costs, and finally, how to avoid the catastrophic failure mode silently killing your compute.
Section 1. Navigating the ravine and escaping those zigzags.
Let's start with the immediate symptom. If your loss plots are showing massive, microscopic zigzags without actual downward movement, you are trapped in that ravine. And look, if you don't understand momentum, you simply don't understand modern deep learning optimization. Without this technique, training a complex architecture like a vision transformer wouldn't just be slow, it would take 10 times longer or just fail outright. Plus, if you're working with LLMs, you have to know that the Atom Optimizer's very first moment is quite literally just this momentum concept. You've got to understand this to tune your models.
Section 2. The Physics of Momentum.
Let's rewind a bit to fix our engine. Back in the 1960s, engineers hit a massive computational brick wall. Getting fast convergence without zigzags required second-order methods, which meant calculating and inverting massive Hessian matrices. For a million-parameter network, that's a million-by-million matrix. Completely impossible. But in 1964, Boris Polyak had this absolute game-changer of an insight, the heavy ball method. He realized that instead of doing impossible math, we could just simulate physical inertia. By making the optimizer act like it has mass, we get second-order speeds at first-order memory costs.
Section 3. The velocity vector math.
So translating that physical weight into math our GPUs can actually process requires a state variable called the velocity vector. By wrapping around vanilla gradient descent, this equation dictates that we take steps using our accumulated velocity, our inertia, rather than just the raw, short-sighted current gradient. It's an exponentially weighted moving average. This means the optimizer isn't just looking at the slope immediately under its feet, it's remembering an average of its last several steps to decide exactly where to go next.
Now visualize that velocity arrow in action over 3 iterations. On step 1, the initial gradient pulls sharply and a small velocity arrow starts growing out of your weight vector. But watch what happens in iteration 2 when the gradient violently reverses direction because we hit the ravine wall. That velocity arrow has grown long. Because of its sheer length, its momentum, it fiercely fights that sudden change in direction. It acts as a massive dampener on the zigzag. By step 3, the lateral bouncing is almost entirely smoothed out, and all that arrow's energy accumulates as pure forward speed down the center of the ravine. You've turned wasted compute into acceleration.
Section 4. The PyTorch tuning dial.
Let's talk implementation. When you type momentum equals 0.9 into PyTorch, I want you to stop thinking of it as just a math constant. You are turning a literal friction dial for your model. Set it to 0.99 and you've dropped your model onto pure ice. It'll slide forever and wildly overshoot the minimum. Set it to 0.5 and it's like dragging it across thick carpet where it stops dead. But 0.9, that tunes the dial to a polished wood floor. It is the absolute sweet spot for preserving inertia without losing control.
But here is a massive diagnostic warning for your PyTorch users. If you're trying to recreate a research paper, you must know that native PyTorch SGD omits the theoretical 1-beta scaling. It injects the raw gradient directly into the moving average. Because of this, your effective momentum window is way larger than the whiteboard math implies. If you just copy a paper's parameters blindly, your training will likely drag, and you usually have to manually dial down your learning rate to compensate for this unscaled gradient injection.
Section 5. Deep learning hardware costs.
Of course, this physical inertia isn't free. It exacts a brutal toll on your hardware. Optimizer steps are notoriously memory-bound, and breaking down the VRAM perfectly explains why. Tracking momentum strictly doubles your state memory. Take a 7 billion parameter model. The weights take up 14 gigabytes. Gradients take another 14. But because Atom tracks momentum and velocity, you are forced to dedicate a staggering 56 gigabytes of VRAM just to those velocity buffers. This physical toll is literally the reason 8-bit optimizers were invented, to compress this massive, expensive momentum state.
Section 6. Avoiding failure modes. Because it's so mathematically heavy and stubborn, mismanaging this state leads to the exact catastrophic failures I see in training logs all the time. Let's diagnose 3 common ones. First, the fine-tuning trap. If you load a pre-trained model for a new dataset and your loss instantly spikes to nan, you've fallen in. You forgot to reinitialize the optimizer state. Your velocity buffer still holds the violent momentum from the old dataset, throwing your weights right off a cliff on step 1. Second, overshooting. Use a 0.99 beta on a simple dataset like MSI and ANIB IT, and your loss will just bounce around the bottom forever without converging. And third, custom loop bottlenecks. Never write your own momentum update with standard Python operations. It forces your GPU to read and write intermediate results to global memory. PyTorch's native optimizer uses fused C++ and CUDA kernels to do this all in one insanely fast pass. Use them.
Which brings us to the bleeding edge of optimization. Given how much memory this polished wood friction dial costs us at scale, again, 56 gigs for a relatively small LLM, we really have to ask, will the next generation of AI architectures discard the bowling ball entirely? Researchers are already developing optimizers like Lion, which throw away the magnitude and rely entirely on the sign of the momentum to save compute. So as we push into trillion parameter models, will physical momentum always be required to navigate the ravine, or is the heavy ball destined to become a relic of the past? Think about that next time you spin up a training run. Thanks for joining me on this explainer.